of the voltage. Peak value of the voltage. So these peak responding voltmeters are classified into two types. One is DC coupled peak responding voltmeter and the other one is AC coupled peak responding voltmeter. So this figure A shows DC coupled peak responding voltmeter and B shows AC coupled peak responding voltmeter. In both the voltmeters, you will be using DC amplifier only, but the position of the diode and the capacitor will be changing. So now suppose take first one that is DC coupled peak responding voltmeter. Now I am going to discuss. So whenever you apply an input voltage here, if the input AC voltage will consist of a positive wave as well as a negative wave. When the positive voltage is applied to the diode anode terminal, then what happens is the diode becomes forward biased. Diode becomes forward biased and it is supplied to the amplifier. So during that interval, the capacitor C1 will be charging position and the applied and that means the diode is forward biased, it is rectifies the AC signal and provides the DC signal. The obtained DC signal is of having less strength, so that less weak signal are amplified by using the DC amplifier, and the peak value is indicated by the instrument here. And when the negative, when only the peak value comes, this will be indicating. During the negative cycle, what happens is the diode will not rectify, and during that the capacitor will be discharging until unless again next peak value comes over. So that means it will measure only the peak values of the voltmeter, peak values of the voltage which you have applied. Likewise, this is the AC coupled AC coupled peak responding voltmeter. In this position, the input voltage is applied to the capacitor so that only the AC signals will be coming and the diode will be rectifying the AC signal into DC circuit, and it will also show the peak value of the input voltage. But one thing is in this one, the capacitor rating should be like it should have speed charging time. That means the rise time should be more, and discharging time should be where the discharge should happen very slowly. Charging should be very fastly done, and discharging should be slowly done. Likewise, those capacitor has to be chosen here in the peak responding voltmeter. Next one is the RMS voltmeter. In this RMS voltmeter, you need to indicate the RMS value of the voltage. For that, you are using this circuit. This is the block diagram of the RMS voltmeter. In this, you are using two thermocouples here. This is one thermocouple, that is measuring thermocouple, and this is the balancing thermocouple. So these two forms a bridge here. These two forms a bridge. That means whatever voltage it is there here V1, and the same voltage should be there so that the bridge will be balanced. So this can be done in this following process. So suppose now here you are applying an input signal. That input signal is given to the AC amplifier circuit. So what does this AC amplifier does is it will rectify the AC input. It will amplify the AC input and it will provide the strong signals to the resistor here. Resistor in the thermocouple. Then what happens is a voltage V1 is produced at this measuring thermocouple. Because based on that heating effect, the voltage is produced here. So this voltage which is produced here, as it is now in the unbalanced position, the bridge becomes unbalanced, and that voltage is given to the DC amplifier. That DC amplifier will send a feedback to the balancing thermocouple, so that a voltage V2 is produced here. Voltage V2 is produced which is having same heating effect as that of the measuring thermocouple. So both are having same voltage and same heating effect. Now the bridge becomes balanced. And the output of the DC amplifier indicates the RMS value. So RMS value means when you give an AC signal, the amount of heat produced with the DC signal, that is the RMS value. So that this RMS value is indicated by using the PMMC galvanometer. So this galvanometer shows the RMS voltage of the input signal. This is about the RMS voltmeter. Next one is a digital frequency meter. So digital frequency meter means this meter measures the frequency and shows the output in terms of digits. So that is the digital frequency meter. And the principle of operation of this digital frequency meter is like this. So here you are using a NAND gate here. We know that for an AND gate there are two inputs. So in those inputs, one input is given with a train of pulses. That a number of pulses, a train of pulses is given for the one input, and for the other input you are providing only a single pulse having 1 second or whatever time period you can choose. So for 1 second, how many pulses are there? For 1 second, how many pulses are there are given as the output here. Now in this 1 second there are 7 pulses coming here, 8 pulses. 7 pulses are coming here. So that means the frequency of this is 1 by 7. That this is the frequency. Likewise, will be because the time period is inverse of the frequency. So for 1 second, how much pulses there it is going to get? That indicates the frequency. And next, the basic circuit for the frequency meter is first whatever the unknown frequency, whatever the frequency which you need to measure, that is given to the amplifier first. So this amplifier will strengthen the weak signals into strength signals. So these both are sine waves only. That's sine waves are provided to this Schmitt trigger. So the purpose of this Schmitt trigger is it will convert the sine wave into a square wave. It will convert the sine wave into a square wave, so that these square wave are fed to the start stop gates. So when these start stop gates are provided with the pulses, so these pulses are counted here in the counter. This is the digital readout. So here the output will be displayed on this digital meter. So whatever it is showing here, that indicates the frequency. So whatever the unknown frequency is provided to the amplifier, that is amplified and that signal is provided to the Schmitt trigger. From that you are getting the square waveforms. Those square waveforms are given to a gate pulse, so that through that gate how many number of pulses are traveling in 1 second. Those are counted in using the digital counter. So that is shown by the digital frequency meter. So this is the basic circuit, and the normal circuit will be like this. So here, as we know that this is the input signal that is fed to the amplifier, and from the amplifier we will be getting the strengthened signal, and that is given to the Schmitt trigger, so that a train of pulses are produced. Initially here there are square pulses, then these square sine pulses, these are converted into train of pulses here, that is given to the one terminal of this gate, and other terminal of the gate is nothing but the gating pulse. This is produced by using a time-based generator, time-based selector. So what is the meaning of this time-based selector? So initially here you are using a 1 megahertz crystal oscillator. That means the frequency obtained here is 1 megahertz. So that 1 megahertz sine wave is given to this meter trigger, so that you are produced with a square waveform. So here it is 1 megahertz. So 1 megahertz means in terms of time period it will be given 1 by 1 megahertz means 1 microsecond. So this consists of number of tappings here, time based selector. So this is 1 microsecond, and if you divide 1 microsecond divided by 10, you will be getting 10 microsecond, and next again 100 microsecond, next 1 millisecond, 10 millisecond, 100 millisecond, 1 second. So likewise, different tappings are there here in the time based selector. So that when whatever time you want to select, whatever the reference pulse, that is gating pulse you want, you can select by using the time based selector. The time which you have selected is given to the Smith trigger, so that it will arrange the number of pulses in one time period, and that is given to the gating flip flop, so that the gating signal is produced to the AND gate. So the output of the AND gate will denote the uh, number of pulses number of pulses in this particular gating signal. So that is indicated by the decimal counter and display unit here. So in decimals, in terms of digits, the frequency is displayed in the digital frequency meter. So this is about the digital frequency meter. Okay. So this is the basic block diagram of digital frequency meter. This is important. From this block diagram only you are able to get this second block, this block diagram. So this is the basic circuit in which the unknown frequency is fed to the amplifier. So this amplifier will strengthen the weak signals, and it will produce a sine wave which is having strength signal, that is given to the Smith trigger, so that you are producing a square wave, and these square waves are given to an AND gate, so that the number of pulses are counted and displayed in the display counter. This is the digital readout here. So this is about the digital frequency.